In this example video from paper 2, your structure paper, we are going to look at a graph about the collision between two objects. Let's read the question. A ball B of a mass 1.2 kg travels at constant velocity v, so it's drawn out for you already, colliding head-on with a stationary ball S of mass 3.6 kg. Okay, if you're looking for this is question 2. All right, May, June 2009, paper 2, question 2. So what we have is this one is stationary, ball S is stationary, and ball B is traveling with the velocity B. Frictional forces are negligible. Very good. I probably need to apply some conservation of momentum, but let's carry on with the question. The variation with time t of the velocity of block B before, during, and after the collision is shown in figure 2.2. So this is a VT graph. Now, if you learn your kinematics well in the previous chapter, you will notice a few things. For example, this is the first stage where the velocity is constant. So I'll bet, I guess that here is before collision. Okay, so I guess from here I can tell that V is 4 meter per second. Okay, it's positive 4 meter per second. And then for some reason, the velocity decreases and then increase in the opposite direction. So just so you know, here to here, the velocity decrease, and then here to here, the velocity increase in the opposite direction. So I'll label here for you. This one, velocity decrease. This one, velocity increase, but in opposite direction. So it becomes a bigger and bigger negative number. And of course, this part here, your velocity is 0. Okay. So finally, it will rebound, and then this is four small boxes. So this is negative 0.8 meter per second. So this tells me after collision, this is before, after collision, your ball B will travel in this direction, 0.8 meter per second. Teacher, ball S leh? Ball S, don't know. I don't know what is going on with ball S. But if I'm going to guess, I'm guessing that ball S will travel here lah. Because it's like it's being pushed by ball B a bit. All right. So probably need to find this somewhere later. Okay. So some of you may be thinking, why is it that the velocity will decrease to 0 and increase in the opposite direction? Let me show you a slow motion video of the collision of two objects. Here's a great video from the slow-mo guys. So if you don't know about them, check them out. I will link this video down below. The channel is pretty cool. But what I have behind me is the ball about to collide with its head. So you could see this head as object S and this ball as object B. So observe carefully what happens to the ball. The ball slows down and stops while the head moves in the opposite direction. And if we were to go back to this graph that we have here, we can see the ball will slow down and stop. Okay, so we don't care about the head first. Let us just keep our eyes on the ball. Okay, I'm going to rewind this a bit so you can see. Okay, so at this point, notice that the ball actually moves backwards a bit. So in this case, you can see the ball is moving backwards a bit before gravity pulls it down. There's a slight push in the opposite direction. Okay, so this is what is happening. When the ball is in contact with the face will slow the ball down and push the ball in the opposite direction. So when ball B is in contact with ball S, that contact force will cause ball B to change direction. Okay, all right, so let's start with part A of the question. State the significance of positive and negative values of B. So why is there a negative value? I think I've stated it just now. The reason why V is negative is because ball B is moves in the opposite direction after collision. Speaking of which, I probably should label where it's before, during, and this is before. Everything in the back here is after collision. And then this part here, from here all the way to the point where it changed, which is here. Here to here is during collision. Okay, this part here is during. Okay, let's continue. Part B, I believe. So use figure 2.2, which is the graph, during the collision with ball S to determine the change in momentum of ball B. So if you want to find change in momentum, I can take MV minus MU. But you know your ball B undergo a change like this. It went from 4 meters per second to the right to 0.8 meters per second to the left. So I gotta give some signs. So I think I'll just follow the sign convention given. This is positive. This is negative, right? So I will take 1.2 times 4, which is the initial momentum, and 1.2 times negative 0.8, which is the final momentum. Let's put that inside here. Okay, so this will be 1.2 bracket. Final momentum is negative 0.8 because it's in the opposite direction, minus 1.2 times 4. So if I press my calculator, it's 1.2 times 4.8. This will give me negative 5.76. They might be thinking, teacher, why negative? What does negative mean? It means that the change in momentum is in the negative direction. It also means that the force is in the negative direction. So if you think of momentum as a vector, then the change in momentum is also a vector. This negative here shows that the change in momentum is to the left. Okay, moving to the left. All right, the opposite direction. So part 2, calculate the magnitude of the force acting on ball B. So you should know by now from Newton's second law, force is change in momentum over change in time. Rate of change in momentum is better, but this is good enough. So to find the force, I need to find the change in momentum, which is negative 5.76. I found it in the front part, divided by the time. Well, we know the time during collision. Okay, during collision, this is the time. The time frame is starting for the point where the velocity dropped all the way until the velocity reached the negative 0.8. So if I'm going to read the time carefully, this is 1, 2, 3, 4, 5, 6, 7, 8. 8 boxes. So 0.08. Okay, the time from here to here, 0.08. Okay, I'm going to pop that into the equation because this is the time taken for the momentum to change from positive 4 velocity to negative 0.8 velocity. The time taken to go from positive 4 to 0.8 negative. That's why I can put 0.08 here. Okay, let's put that in 0.08. And finally, I will get my force as 72 Newton. Okay, so this 72 Newton, there's a negative here. And then why is there a negative there? Same reason. No? This negative here shows that the force on ball B is to the left. Let us verify by drawing the balls again. You have B like this, and you have S like this during collision. Okay, so during collision, I know they will distort, but I didn't draw that, so it's okay. S will push B, right? The force of S on B will be in this direction. So this is the force of ball S acting on ball B. Negative 72 Newton. This means the force of ball B on ball S, according to Newton's third law, F of B on S, is also 72 Newton, but it's going to be positive. Okay, it's going to be positive. So the reason to that is because Number one, ball B has a negative change in momentum, negative 5.76. This actually tells us, right, when the ball reaches B, okay, opposite direction, when the ball reaches B reaches S, sorry, when B reaches S, it will go back in the opposite direction. That change in momentum is the negative direction. Okay, so when it travels in the opposite direction. So if I put it together, all right, here it is, I draw already. Okay, so this is before, this is during that time there's forces interacting between them. And if you just look at B, okay, let me just highlight my B. Okay, we just look at ball B. Ball B experiences a force from S. That's why the momentum of B change. Okay, so you want to talk about conservation momentum, can, provided there's no external force. So if you look at B alone, B got external force from S. So if you look at B, the momentum is not conserved. And if you look at S, the momentum of S also not conserved. But S was here chilling, and then B come and whack it, and then now S will have to move in probably this direction, because S experiences a force of B in the right direction, positive 72 Newton. Okay, so if you want to think about conservation of momentum, let me type down a few statements for you regarding to this drawing. Okay, number one, momentum of B is not conserved. Why is it not conserved? Because there is a, due to the force that S is acting on B. So momentum of A, not conserved. B, not conserved. And because of this, we can also say momentum of S also not conserved. Why is the momentum of S not conserved? This is due to force of B pushing on S. And these two forces are equal magnitude, opposite direction. Force of S on B is equal to force of B on S. The magnitude-wise, magnitude is the same, thanks to Newton's third law. This is N3. Okay. And finally, if you want to still apply conservation of momentum as we normally would, can, but you have to take ds as your whole system. Cannot just take B, cannot just take S, must take B and S together. So the momentum of B plus momentum of S is always conserved. Teacher, no force meh? Got force, not external. Because if you take B and S as one system, then it includes the force. Or the resultant force is zero, because, negative 72 and positive 72. Okay. Cannot really say resultant, but there's no external forces. So PB plus BS is conserved. So I will just say it's conserved. And the reason why it's conserved is because there is no external force. That's why whenever you define conservation of momentum, you must write down the condition. There's no external force, because FSB and FBS are not external anymore. They are part of the system. Part of this BS system. So whenever we do kinematics, right, analysis, it's good to stop and ask ourselves, what is our system? If our system is B alone, then it's not conserved because there is the force of S on B. B and S got interaction. If it's the momentum of S alone, it is also not conserved. This is thanks to the force of B on S. Okay? And the magnitude of the force of SB and BS must be the same. And the final point here is, normally we do this. We conserve momentum, can, if we take the whole system as B and S together. So if your system is B plus S, then the momentum is conserved, because these two forces we consider are part of the system. Okay. All right, let's go back to the question, because here it says, calculate the speed of the ball after collision. So you could use the third point where I say the magnitude of the forces is the same, you could use the fourth point where the momentum is conserved. I'll show you both. Okay. So the method will be the force of ball B on ball S is also 72 Newton. Okay. So I can take the change in momentum of ball S over the contact time. Contact time must still be the same, 0.08 seconds, because how can B touch S without S touching B? That's just weird, right? It's like someone touch you, but you're not touching that person. Very weird, very weird. No haunting of nothing, no haunting here. Okay, so we can find the change in momentum of S. But if you remember, your S was initially stationary. Let me scroll here a bit so you can see your S. S was initially stationary. And let's say after the collision, it has a speed of V. I don't know what this V here is. We're going to find it. Okay, so the initial momentum is 0. The final momentum is S, the mass of S times V. And if you forget the mass of S, you are given here, 3.6 kg. Okay, so I'll put that in here. Meaning to say this will be 3.6 times V. If you want to, you can obviously put minus 0. Okay, this will be equal to 72 times 0.08. So from here, I can find V law. 72. This is 5.76 divided by 3.6 is equal to 1.6 meter per second. All right. An alternative would be to use conservation of momentum. Or, okay, so I can do sum of the initial momentum is equal to the sum of the final momentum. Zoom in a bit for the people at the back with small screens. Okay, the initial momentum, only S is moving, right? So S is here. Sorry, only B is moving. So I'll take the momentum of B, which is 1.2 kg. Momentum of B multiplied by the initial speed. Okay, so for S is not moving, so it's 0. Then I'll take the momentum of B after collision, 1.2 times negative 0.8, okay, plus the momentum of S, so that would be the mass of S, which is 3.6 kg, multiplied by V. So if you press your calculator, I'm pretty sure this one will still get you 1.6. In fact, if you examine the working, you chop for a while and think about the working for. This 1.2 times 4 plus 1.2 times 0.8 is your 0.76. So the change in momentum of B is also equal to the change in momentum of S. Many ways to look at this. Okay, so you solve in whichever way that makes sense. This means that I can add another point here in my 4-point, or a caveat, side note here. The change in momentum of S will be equal to the change in the momentum of, okay? Because the contact time is the same. It's a bit like our total change is the same. So if the momentum of B is negative 5.76 Newton second, then the momentum for S will be positive 5.76 Newton second. They have the same magnitude because the contact time is the same. Then when you total up, is there any change? No. So if there's no change, this means directly I can say that the momentum of PS and TB is conserved, because you can see start 5.76, your change positive 5.76, my change negative 5.76. So put together in the system, got change or not? No. Hence, the momentum is the same. So Newton's law help us explain conservation of momentum. Conservation of momentum complements Newton's law. They are both the same thing. Make sure your ideas are there, okay? They are not different things. They are the same. So how you choose your system is up to you. Okay, you want to look at B alone, then momentum not conserved law, got external force. You want to look at S alone, then momentum not conserved law, got external force. But These two external forces are actually equal magnitude thanks to Newton's third law, and they will have the same change in momentum because, the momentum is conserved if you take both of them together. Next part of the question. Using your answer in C and the information from the graph, deduce quantitatively. So when I say quantitatively, it means use numbers. Use numbers. Whether the collision is elastic or inelastic. So if you want to use numbers, right, you want to put down numbers to know whether it's elastic or inelastic, you got two choices. You could either find the kinetic energy or you could use the relative velocity equation. So I'm going to show both. I will find the KE before collision. So I'll write here initial kinetic energy. And this will be half mass of B. So if you've forgotten what B is, how could you? Okay, anyway, it's a bit laggy, yeah. 1.2 times 4. But S got no kinetic energy. So I put inside here, 1.2 times 4 squared. And then I find the final kinetic energy. 1.2 is now moving at 0.8 meter per second, but the 3.6 kg is also moving. Is it 3.6? Yes, 3.6 kg. Moving at 1.6 meter per second. So we find both value of kinetic energy and we compare them. 0.5 times 1.2 times 4 squared. This is 9.6 joule. Then I repeat the same calculation after collision. The 1.2 kg ball or ball B is now traveling at 0.8 meter per second. And then the 3.6 kg ball S is now traveling at 1.6 meter per second. This is 4.99 joule. This is about 5 joule. So now you can conclude already. Since the kinetic energy is not conserved, because initial and final not the same, not conserved, I can say that the collision is inelastic. I find this one more straightforward, but some people, you may prefer to use relative velocity. So you could say, you could recall the relative velocity equation. U1 minus U2 is equal to negative V1 minus V2. Okay, so your ball B was traveling in the positive 4 direction, and your ball S is not moving. Okay, I should use different color for this. And then your ball B, because 1 is B, and 2 is S. After traveling, ball B is negative 0.8 in the negative direction. And then minus V2 is in the positive direction. Okay, so 1 and 2 is your BS. So is it the same? On one side here, you have 4. On the other side here, you will have positive 2, 1.6 plus 0.8. Right? Too many negative signs. 2.4. And they are not equal, right? So your conclusion could be, always make conclusion, okay? You could say that the speed of approach which is positive 4 meter per second, 4 meter per second, is not equal to the relative speed of separation, positive 2.4 meter per second. Hence, collision is not elastic. All right. So you can use KE method 1. You can use relative velocity equation method 2. Make sure you write conclusion. Okay. So where is the marks here? If you calculate both of these correctly, you get 1 mark. You show the evidence though. and then only conclusion. But because this is a M1 mark, meaning if you don't show some evidence, either kinetic energy evidence, then your conclusion, even correct also, you won't get mark. If you don't score the M1 mark, you will not score the A1 mark. Okay, so you either show evidence in kinetic energy or you show evidence in relative velocity. This is M1, then this one, your conclusion is A1. Conclusion must write properly, lor. Don't just say hence inelastic. What you mean inelastic? Must explain what happened. KE not conserved, or the speed approach not equal to speed of separation. All right. The remaining calculation mark scheme is pretty straightforward. You just need to show your equation, your calculation. Okay. Each stick is 1 mark. Show the equation, show the substitution, show the final answer. Show the equation, final answer. Substitution, final answer. All right. So that's it for this example. Okay. I took some time to explain clearly what is going on in the collision, especially the interaction between two balls. Very important to know these ideas because they can test you in different formats. I'll see you in the next example video. Till then, go collide some balls, do more questions. Bye-bye.